All right, strap in, everyone, because today we're diving deep into direct conversion technology. DCT.
Yeah.
You've sent us this research proposal, and it's, well, frankly, it's mind-blowing.
Yeah.
This idea of scaling up, megawatts of power.
Right.
Using heat to light to electricity conversion.
HLE.
HLEC. And also thermophotovoltaic conversion. PVV. So we're talking about, industrial scale energy production here.
Yeah, absolutely.
So let's break it down.
Yes.
What's got us so excited about this proposal?
Well, they kick it off with a really provocative statement from one of the lead researchers, Dr. Levne Moten.
Okay.
And he kind of calls it ridiculous that in this day and age, we're still boiling water to get energy.
Oh, wow.
With all the advancements in physics and, everything.
It really makes you think,
Yeah.
Like, we're sending people to Mars.
Right.
But we're still, using such an old-fashioned way to get energy.
Yeah, it's like, we're in the age of self-driving cars, but we're still using a horse and buggy.
Perfect analogy.
To get around.
So that's where DCT comes in.
Yeah, that's what they're saying.
It's like the modern solution.
Exactly, like a more sophisticated, more elegant way of doing things.
So how is it different?
Well, DCT bypasses the whole steam turbine generator setup that traditional power plants use.
Oh, right.
It's kind of like a shortcut to electricity. A more direct path from the energy source to usable electricity.
I like the sound of a shortcut.
Yeah.
So how does it actually work?
Okay, so both HLEC and TPV, these two DCT technologies, they work by converting heat directly into light and then that light into electricity.
Wow. So instead of heat to steam to turbine to electricity, we're kind of cutting out the middleman.
Exactly. You got it.
Fewer moving parts.
Yeah. Less maintenance, higher reliability.
Potentially lower costs.
Yeah, absolutely.
Okay, but where would we use this technology? What are we talking about? Like, what kind of applications?
Lots of different potential applications.
Okay.
Especially in industries that operate at high temperatures.
Oh, okay.
So, for example, gas turbine power plants, concentrated solar power plants, systems for recovering waste heat from industrial processes.
Wait, so we could actually capture energy that would normally just be lost as waste heat.
That's the idea.
Wow, that's incredible.
Yeah, and it's not just about making things more efficient.
Okay.
They even talk about incorporating DCT into fossil fuel-fired boilers.
Really?
To increase their efficiency and reduce emissions.
Oh, wow, that's interesting.
Yeah, of course. It's not a perfect solution.
Right.
We still need to transition away from fossil fuels.
Of course, yeah.
But DCT could help minimize their impact in the meantime.
Like a bridge to a cleaner energy future.
Exactly.
Okay, well, this is all very exciting.
Yeah.
Let's dive into those two DCT technologies a little bit more.
Okay.
First up, HLEC. How does that work exactly?
Okay, so HLEC systems, they use high temperature thermal radiation to create electricity. So imagine you've got a super hot source, like an industrial furnace.
Okay, got it. Lots of heat.
Yeah.
Lots of radiation.
That heat generates thermal radiation.
Okay, so then what?
And then HLEC systems use advanced optics and specialized PV technology.
Photovoltaic.
Yeah, to capture that radiation and convert it directly into electricity.
But I thought photovoltaics, like solar panels, only worked with sunlight.
Yeah, traditional solar panels are designed for sunlight.
Okay.
But with HLEC, we're talking about special PV cells that can capture a broader spectrum of light.
Okay.
Including infrared radiation.
So it's like a super solar panel.
Exactly.
That can handle some serious heat.
You got it.
So we're turning heat into light and then light into electricity.
That's the basic idea.
Wow. So what are some of the benefits of that?
Well, one of the big ones is that you're eliminating those bulky mechanical components. So that means you can have a system that's more compact, more efficient.
Okay.
And potentially even more cost effective.
Now, what about TPV?
Okay, so TPV...
How does that capture those rays and turn them into power?
So TPV also uses thermal radiation from a high temperature source.
Okay.
But it uses a slightly different approach.
Okay.
Imagine like specialized photovoltaic cells that are tuned to capture specific wavelengths of infrared light.
So both of them are working with infrared light, but TPV is more selective about it.
Precisely. Yeah. They often incorporate what are called selective emitters and spectral control layers.
Okay.
It's kind of like fine-tuning the system so that the PV cells are only receiving the wavelengths of light.
Okay.
That they're best at converting to electricity.
So it's like we're filtering out the noise and amplifying the signal.
Exactly. Yeah.
Okay, so we've got two different approaches, each with their own strengths.
Yeah.
And both have the potential to be way more efficient than traditional methods. Okay, but let's not get ahead of ourselves.
Right.
We have to talk about the hurdles.
Yeah.
We've got to overcome those before this becomes a reality.
Yeah, the challenges.
What kind of challenges are we up against?
Well, material science is a big one.
Oh, okay.
We're talking about systems that operate at temperatures exceeding 1,000 degrees Celsius.
Wow.
Finding materials that can withstand that kind of heat for extended periods is no small feat.
That's like trying to build a spacecraft that can fly through the sun.
Right. Exactly.
So what are they even looking at?
They're looking at some pretty advanced materials.
Like?
Ceramics, metamaterials.
Metamaterials? Wow.
Nano-engineered composites.
Nano-engineered composites.
Yeah.
Wow, this is cutting edge.
Absolutely, and that's just one piece of the puzzle.
Yeah.
They also need to find materials that are resistant to radiation damage.
Okay.
Which can degrade even the toughest materials over time.
Right, so it's not just the heat.
Yeah.
It's like a constant bombardment of radiation. Are there any other challenges besides materials?
Yeah. Thermal management is another big one.
Okay.
Figuring out how to prevent these systems from overheating while still making sure we're efficiently capturing and converting as much energy as possible.
Right. It's like this very careful dance.
It's a delicate balancing act.
Yeah, we're managing this flow of heat and light very precisely within the system.
Yep.
And then, of course, there's cost.
Oh, yeah.
I mean, all of this has got to be pretty expensive.
Right. Bringing the cost down is going to be critical.
Yeah.
If we want to make DCT commercially viable.
If we want this to actually happen.
Exactly.
Okay. Well, this has been an incredible overview.
Yeah.
But, I mean, where do we go from here?
Well, that's where the research proposal comes in.
Okay.
It lays out a detailed roadmap for how they plan to tackle these challenges and develop DCT into a viable energy solution.
Our listeners, we're going to take a quick break. And when we come back, we'll break down those research phases, the brains behind this project.
Sounds good.
And how they plan to make DCT a reality. Stay with us.
We'll be right back.
Welcome back, everyone.
All right.
So we've laid out the potential of DCT, but how do we actually, make this technology work?
Right.
The research proposal kind of outlines this whole multifaceted approach to tackling all of these challenges we talked about.
Yeah.
What, really stands out to you about that?
Well, their materials research is fascinating. I mean, we're talking about systems that operate at incredibly high temperatures under intense radiation.
Right.
So finding the right materials is just absolutely crucial.
But so, what can even handle that?
Well, they're exploring a few different avenues.
Okay.
One is looking at advanced ceramics, which are known for their heat resistance.
Yeah, I mean, they're already used in, all sorts of high-temperature applications.
Exactly.
Like kilns and spacecraft.
Yeah, spacecraft heat shields.
Right.
But they're also looking beyond traditional ceramics.
Okay.
To things like metamaterials.
Oh, metamaterials. Those are so cool.
Yeah, they're engineered to have properties that you just don't find in nature.
Yeah, it's like we can design materials that have specific abilities now.
Right. Imagine materials that can manipulate light and heat in ways we've never been able to before.
Yeah, that's wild.
Yeah. So that's the kind of thinking that we need to make DCT a reality.
So what else are they looking at?
Well, they also mentioned nano-engineered composites. So these are materials designed at the nanoscale.
So we're talking about manipulating atoms and molecules.
Exactly.
To create custom designed materials.
It's like building materials from the ground up.
Right.
To withstand these extreme conditions.
Yeah, that's amazing.
Yeah. And it's not just about heat resistance.
Okay.
They also need to be able to hold up against intense radiation.
Yeah, we were talking about that.
These DCT systems are going to be bombarded with infrared radiation, which can,
It can mess stuff up.
Yeah, it can degrade stuff over time, even the toughest materials.
Right. So it's like a suit of armor that can withstand fire and lasers.
Exactly.
Okay, so materials research, big part of this.
Huge part, yeah.
But what about, the design of these DCT systems?
Yeah.
Are there any, innovative ideas on that front?
Oh, absolutely.
Okay, tell me.
One concept that really caught my eye was the gaseous heat absorption blanket.
A blanket made of gas.
Yeah, no, it sounds kind of weird.
Yeah.
But basically, imagine a layer of high-density gas, like xenon or argon, surrounding the heat source.
Okay.
And this gas would be designed to absorb the thermal energy from the source.
Okay.
But it would remain transparent to specific wavelengths of infrared light.
So it's like a filter?
Yeah, exactly.
Oh,
only letting through the useful light.
Wow. Okay. And what about the emitters themselves? Are there any, like, big advancements there?
Yeah, so they're proposing to use something called volumetric 3D infrared radiation.
Okay, break that down for me.
So instead of having a single centralized emitter,
right,
they want to create like a network of gas-filled chambers that emit infrared light in all directions.
Wow, so it's like this distributed network of tiny emitters.
Exactly. This could lead to more uniform heat distribution, and it could potentially increase the surface area available for light emission.
Yeah, that makes sense.
They're also exploring the use of gaseous light-emitting panels.
Okay.
So imagine like panels filled with a special gas mixture that converts absorbed heat into a 3D omnidirectional source of infrared light.
Okay, so they're really like pushing the boundaries of what's possible with light emission.
They're really trying to optimize every component for maximum efficiency.
Right, because it's all about energy transfer in the end.
Yeah, it's all about energy transfer.
Okay, so what are they doing on that front?
Well, they're proposing to use microfluidic or aerosol-based systems to control the flow of heat and light within the DCT system.
So it's like a microscopic plumbing system.
Yeah.
For heat and light.
You got it.
Okay, so they've got the materials. They've got these innovative design concepts.
Right.
Who are the people behind this?
Well, the proposal outlines a collaboration between two research teams.
Okay.
One in the US from N5 Digital.
Okay.
And the other from Israel, from the Technion Israel Institute of Technology.
So we've got a global team of experts on this.
It's a really interdisciplinary effort.
Okay.
Bringing together specialists in material, science, thermal and optical engineering, computational modeling.
Wow, the whole shebang.
Yeah, and prototype manufacturing and testing.
Wow, so they've got a real dream team here.
They do, and they've got some great leaders, too.
Yeah, like who?
The proposal highlights Dr. Ezra Elias from Technion.
Okay.
And Dr. Lev Nemotin from N5 Digital as the lead coordinators.
Right. Okay, so we've got the vision, we've got the technology, the people to make it happen.
Right.
But let's be real. Research and development on this scale takes a lot of time and a lot of money. How are they planning to, like, turn this ambitious project into a reality?
Well, they have a 3-phase approach for research and development.
Okay, break it down for me.
All right, so each phase has its own goals, timelines, and budget. It's a very structured approach.
Yeah, because this is a very complicated project.
Exactly.
So phase 1, what's the focus?
Phase 1 is all about laying the groundwork.
Yeah.
It's the feasibility study.
Okay.
It's set to last 18 months.
Okay.
With a budget of $3 million.
Okay.
During this phase, they're going to focus on theoretical evaluations, spectral optimization, and identifying any potential roadblocks.
So it's like the blueprint.
Exactly. For the entire project.
Yeah.
Okay, so a lot of computer modeling, simulations, that kind of thing.
Lots of preliminary experiments.
Okay, so then phase 2.
Phase 2 is where things get really exciting.
Oh, okay.
This is the laboratory experiments and prototype development phase.
Okay.
And it lasts 24 months with a budget of $25 million.
All right, so the stakes are getting a little higher.
Yeah, things are ramping up.
What are they actually doing in phase 2?
Well, this is where they take those theoretical models and start testing them in the real world.
Okay.
So they'll build high-temperature test beds to simulate real-world operating conditions. They'll develop and test those PV arrays, and they'll build a lab-scale prototype of the entire DCT system.
So we're going from computer models to like an actual working model.
Exactly.
That's a big jump.
It is, yeah.
What are the main goals for this phase?
Well, I mean, the main thing is proving that it can work.
Right.
Not just in theory, but in real life.
They'll also be integrating those advanced cooling and photon recycling systems.
Right.
We talked about that earlier.
We did, yeah. It's about capturing and converting as much energy as possible.
Every photon counts.
So phase 2 is all about fine-tuning.
Yeah. Making sure it can operate efficiently and reliably.
Okay. And then finally, phase 3.
Phase 3 is all about scaling up.
Okay.
And preparing for industrial integration. It lasts 18 months with a budget of $22 million.
So this is taking what they've learned from the prototype and figuring out how to make it work on a massive scale.
Exactly, yeah. So they'll be conducting those large-scale simulations to optimize the design for industrial applications, and they'll be developing detailed plans for integrating DCT into existing power plants.
Okay, so it's bridging the gap between research and real-world application.
Exactly.
Okay, so we've got a plan for research and development, but $50 million.
Yeah, that's a lot of money.
That is a significant investment.
It is.
How are they going to finance this whole thing?
Well, they're exploring a variety of funding sources.
Okay.
Government grants, private investment, venture capital, corporate partnerships.
So they're casting a wide net.
Yeah, they're leaving no stone unturned.
Okay, what's the strategy?
Well, first, they're going to reach out to government agencies that focus on funding energy technologies.
So things like ARPE.
Exactly, yeah, and the National Science Foundation.
Right. Okay, so government support for cutting-edge science. What else?
They're also seeking partnerships with companies in the energy sector, not just for funding, but for their expertise, and also potential pathways to commercialization.
Right, so if they can get industry leaders on board early on, it'll be much easier to bring it to market.
Yeah.
Okay, what about other funding sources?
Well, they're also exploring venture capital, particularly from firms that specialize in clean energy.
Okay.
And they'll be leveraging Dr. Neymoten's expertise.
And his team at N5 Digital to connect with potential corporate partners.
So it's kind of this three-pronged approach. Yeah. It's really interesting. It reflects, I guess, the complexity of the project.
Absolutely.
And just the massive potential.
It has huge potential.
Okay, so we've talked about the materials, the design, the team, and the funding.
Yeah.
What are your takeaways so far?
Well, I'm really impressed with the ambition and the scope of this project.
Yeah.
I mean, they've really thought through every aspect of it.
Yeah.
From the fundamental science to the practical challenges of scaling it up and commercialization. It's clear that they're really serious about making this happen.
It's not just about the technical stuff either, right?
No, not at all. The potential impact is huge.
Yeah.
You know, if they succeed, this could totally transform how we generate and use energy.
Yeah.
It could lead to a more sustainable future.
Yeah, I'm with you. More efficient future for everybody.
It's a vision worth striving for.
Absolutely.
All right, everyone. In part 3, we're going to talk about the potential applications of DCT.
Okay.
And what it could mean for our energy future.
Sounds good.
Stay with us. All right, welcome back, everyone. We've spent the last 2 parts, really getting into the science and the engineering behind DCT, but now I want to talk about what it actually means.
Yeah.
For, industries.
Right.
For the world. Like, what are we really talking about changing here?
Well, DCT has the potential to revolutionize a whole range of industries that rely on high-temperature processes.
So, give me some specifics, paint me a picture.
Okay, sure.
What kind of impact are we talking about?
Well, let's start with power plants.
Okay.
I mean, many power plants, especially gas turbine power plants, they rely on heat to generate electricity.
Okay.
But by incorporating DCT, those same plants could operate at much higher temperatures, which means they could squeeze out a lot more efficiency.
So we're not even talking about building new power plants.
Not necessarily, no.
We're talking
about making the ones we have work better.
Making them more efficient.
Exactly.
Okay, so that means less fuel.
Less fuel.
Smaller carbon footprint.
Yeah.
Potentially lower costs.
Potentially lower costs, yeah.
Okay, so that's a win-win.
Yeah.
What other industries could benefit?
Well, think about concentrated solar power plants.
Okay.
They use mirrors to focus sunlight, creating intense heat.
Yeah.
DCT could convert that heat directly into electricity, which would potentially make these systems even more efficient.
So we're talking about harnessing the power of the sun.
Yeah, absolutely.
Even more effectively. Okay, what else?
And then there's waste heat recovery.
Waste heat recovery.
So many industrial processes generate tons of heat as a byproduct.
Oh, right. Okay.
Steel mills.
Yeah.
Glass factories, data centers.
Okay, yeah.
All this heat.
Just being wasted.
Yeah, basically just being wasted.
Wow.
DCT could capture that heat and turn it into electricity.
That's like getting free energy.
It's kind of like that, yeah.
Okay.
It's about making these industries more sustainable, more cost-effective.
Right.
Doing more with less.
Okay. So...
And here's where it gets really interesting.
Okay.
The proposal even suggests that we could integrate DCT into fossil fuel-fired boilers.
Really?
Yeah.
To make them more efficient.
Yeah, to make them more efficient and cleaner.
Okay, so even while we're trying to move away from fossil fuels, this could help in the meantime.
Exactly. It's not a perfect solution.
Right.
But it's a step in the right direction.
So we've got power plants, solar, industrial waste heat, even fossil fuels.
Yeah.
I mean, this really does touch everything.
It has the potential to touch a lot of different things.
Yeah.
And that's just the beginning.
Okay, so what's next?
I mean, think about the broader implications. If we can scale up DCT, it could really change how we think about energy.
Okay, I like that. I like where this is going.
Yeah.
Paint me a picture of that future.
Okay, so imagine a world where power plants are smaller, they're more efficient, and they generate less waste. A world where we're not just using energy, but we're reusing it, we're capturing it from all these different sources.
Right. It's about sustainability.
Exactly.
It's about, not just resources, but the environment too.
Absolutely. And it could also enhance energy security.
Oh, okay. How so?
Well, it could allow for more distributed power generation.
Okay.
So instead of relying on these huge centralized power plants, we could have smaller modular DCT systems located closer to where the energy is needed.
So each building or each neighborhood could generate its own power.
Potentially, yeah.
Wow. That's a very different future.
It is, yeah.
Than what we have now. Okay, but I have to ask.
Yeah.
What are the downsides?
Right.
I mean, every technology has downsides.
Of course, yeah. We need to be realistic about that.
So what are we talking about?
Well, cost is a big one.
Right? We talk about that.
The materials and the manufacturing processes, they're still pretty expensive.
Right. We got to make it affordable.
We do, yeah.
If this is going to be something that everyone can use.
Exactly. And then there's reliability, durability. I mean, these systems are going to be operating under extreme conditions.
Right. They got to be built to last.
They do. And we also need to think about the environmental impact of the entire life cycle,
Yeah.
From materials to manufacturing.
Disposal.
And disposal, yeah.
Right. We don't want to solve one problem and create a new one.
Exactly.
Okay. Well, this has been quite a deep dive.
It has.
We've talked about the science, the challenges, the vision of the future.
It's a really fascinating technology.
It is. And even with all the challenges, it's really hard not to get excited.
Yeah, I agree.
About the potential.
The potential is huge.
Yeah.
And I think the research they're proposing here is a really important step towards making that future a reality.
Absolutely. Well, listeners, that brings us to the end of our deep dive into the world of DCT. We've explored a lot today.
We have.
But before we go, we want to leave you with a question.
Okay.
The proposal really focuses on certain applications.
Right.
But what other possibilities are out there?
Yeah. What else can you imagine?
Could this be used in transportation? In space exploration?
Yeah, maybe even everyday devices.
Yeah, it's a really interesting question.
It is.
And who knows, maybe one of you listening will be the one to unlock those possibilities.
Yeah, it would be great.
The future of energy is full of potential.
It is.
And DCP could be a key part of making that future brighter, more sustainable, more efficient for everyone.
Thanks for joining us.
And until next time, keep those minds curious and those imaginations firing.